Learn like a pro.
All right, let's dive right into the mechanics of power. You know, we talk a lot about energy, but having energy isn't the whole story. What really matters is how fast you can use it. And that speed, that rate of delivery, well, that's what power is all about. Okay, think about this for a second. A tiny little firecracker and a big log for a fireplace can actually contain pretty much the same amount of chemical energy. So why is one a sudden loud bang and the other is just a slow, gentle burn that lasts for hours? What gives? The answer to that question gets the very heart of what we're talking about today.
You see, the secret isn't about the amount of energy. It never was. It's all about the speed at which that energy gets out. It's a story about how fast you can make the transaction.
Take a look at this. It's a fantastic way to picture what's happening. Imagine we have two identical vaults, right? Each one is holding the exact same amount of energy. The vault on the left, though, it's got this skinny little pipe. The energy is trickling out, slow and steady. But the one on the right, it has a massive pipe, and it's unleashing that same amount of energy in a huge, sudden rush. Same total energy from both, but that one on the right is just way more powerful. And that brings us right to the formal textbook definition. In physics, power is simply the rate at which work gets done, or the rate that energy gets transferred. It's not about how much energy you have locked away in the vault. It's all about the size of the pipe you're using to let it out.
So, if power is all about speed, how do we actually measure it? How do we put a number on that thick pipe to show just how fast that energy is flowing?
Well, the most straightforward way is with this simple, beautiful equation. Power equals energy divided by time. P equals E over T. It perfectly describes our vault analogy, doesn't it? E is the total energy you're transferring, and T is how much time it takes. So if you move the same amount of E in a much smaller T, you get a much bigger P. You get more power. Simple as that.
And the standard unit we use for this is the watt. And here comes our friendly unit guard to make sure we get this right. 1 watt is officially 1 joule of energy being used every single second. So when you see a 100-watt light bulb, what that really means is it's converting 100 joules of electrical energy into light and heat every second it's switched on.
But wait, there's another, equally powerful way to look at, well, power, especially when things are moving. This next angle connects power directly to two other huge concepts in physics, force and velocity.
Now, this isn't some brand new idea pulled out of thin air. It's actually built right from what we already know. So, stick with me here. We start with power equals work over time. We got that. But hang on, remember what work is? It's just force times distance. So let's swap that into the equation. Now we have power equals force times distance all over time. And this is the cool part. Look closely. What's distance divided by time? That's velocity, which means power is also equal to the force you apply multiplied by the velocity you get. P equals F times V. It's so elegant.
So what does that actually look like in the real world? Think about driving a car. To just cruise along at a steady, low speed, your engine only needs to produce a little bit of force to balance out friction. That's a low power output. But if you want to fly down the highway at a really high speed, you're fighting way more air resistance. The engine has to generate a massive force just to keep you going, and that demands a huge power output.
Okay, enough with the theory. Theory is great, but let's get our hands dirty. Let's apply these formulas to a real-world problem and see how it all shakes out. Here's our setup. We've got a 50-kilogram girl, and she climbs a 4-meter flight of stairs. It takes her exactly 10 seconds. The question is, what's her power output? We're going to solve this in 3 logical steps. First, we'll figure out the force she's fighting against. Second, we'll calculate the total work she did. And finally, we'll bring in the time to find her power. Step 1, the force. The main force she has to overcome is her own weight, plain and simple. We find that by multiplying her mass by the acceleration due to gravity, which we'll call 10. So 50 kilos times 10 gives us 500 newtons. That is the constant force she has to push with just to move upwards.
Step 2, let's calculate the work done. Now, work is just that force multiplied by the vertical distance she traveled. So 500 newtons times 4 meters, that gives us 2,000 joules. That's the total amount of energy she had to transfer from her body into gravitational potential energy.
And finally, step 3, let's get the power. We know she did 2,000 joules of work, and we know it took her 10 seconds. So we just plug those numbers into our first formula. Power is work, or energy, divided by time. 2,000 joules divided by 10 seconds, and that gives us our answer.
And there it is, a power output of 200 watts. You can see it right there on our power gauge. To climb those stairs at that speed, her body had to generate energy at a rate of 200 joules every single second. That's pretty impressive.
So now let's just zoom out for a moment and see how all these different pieces we've been talking about, force, work, energy, and power, all lock together into one beautiful, unified system. This flowchart just nails it. It all starts with a force acting over a distance. When you combine those two, you get the action, which is work done. Now, doing work is how we transfer the universal currency, which is energy, and finally, when you look at how much of that currency was transferred and divided by the time it took, you get the rate of exchange. And that rate is power.
So, if you remember just one thing from all this, let it be this simple idea. Energy is what you have in the bank. It's the potential. But power is how fast you can spend it. It's the difference between a slow burn and a massive explosion. It's not just about what you've got, it's about how fast you can use it.